Thanks everyone for coming today. It's really, really cool for me personally to see people back on site for QHack. The very first QHack, as was mentioned earlier, was at our office here in downtown Toronto, upstairs, and that was in 2019. And so it's really nice to welcome everyone back and to see all these faces in person. And I hope that you can enjoy our office space, enjoy talking to our team, and I'm looking forward to meeting all of you. So today I'm going to give a talk that represents some of our current thinking about the field of QML, and maybe it's a bit more critical than some other works out there. So I want to maybe just cause people to think a little bit more carefully about the fields. My goal here is not to provoke, but maybe to just inspire you to be thoughtful about the papers you read. So there will actually be a paper representing this talk on the archive soon. The paper's coming together. It should be out in the next month or so, so watch for that. So everything here is preliminary results, a sneak preview. The main message of the paper is not going to change between now and then, but some of the final data might come in or be improved. We've got lots of great quantum machine learning researchers here at Xanadu across a couple teams. I myself contribute, but we also have a number of strong people on the team. This particular project that I'm speaking about today represents the work of Joseph, Shanoaz, and Maria primarily. They're the ones who are doing a lot of the really hard stuff here to bring these results to us. So full credit to them. I'm representing their work today. Generally, it's really easy to say, well, QML research, the goal of QML research is to make quantum computers useful for machine learning. That's very, very, pie in the sky kind of way of thinking about it. But when quantum computers were first dreamt of in the 90s, let's say, the state of play for computer science, for programming, for just computers in general was much different than it is today. By the time quantum computers are reaching a large-scale, fault-tolerant regime, the surrounding background of computer science and computing technology that they find themselves in will have drastically shifted. There's a huge, huge growth in AI, in machine learning. These kind of things are going to be, background standard stuff that everyone learns about and everyone kind of takes for granted. So we should make sure that quantum computing fits nicely into that world it's going to emerge within. So quantum machine learning, that's why we pursue quantum machine learning here at Xanadu. We think it's going to be kind of essential ingredient if we're working on quantum computers, and computers are going to be pretty highly connected with machine learning ideas. QML is a very, very broad field. It can mean lots of things. Just to really simplify scope, we're just going to talk here about the notion of solving machine learning problems using quantum computers. There's other ways you could kind of combine machine learning and quantum, but that's what we're going to talk about here. And then we can break that down into kind of two main schools of thought. There's the subset of algorithms that work on fault-tolerant quantum computers. These are kind of idealized quantum computers. You can imagine any number of qubits you want, full error correction. These, there's lots of papers of these historically. The general trend is maybe to take a part of a machine learning computation and outsource that to a quantum computer. That's the general flavor of these kind of fault-tolerant subroutines. And then more recently, we have this NISQ era, which may be hitting the end of its peak. The real trend setter in the NISQ era was these variational circuits. These are quantum circuits where the quantum circuit itself is the model. It's not just outsourcing a subroutine of a larger pipeline, but it itself is the model, or a significant portion of it. And we study the properties of these quantum circuits as machine learning models or through a machine learning lens. So how do we know if we're researching the right things, if we're making progress, right? In AI, they have tons of data sets, they have huge compute power, they have real-world problems that they can test things on at scale. We don't have that in quantum machine learning. We're stuck with some other tools that are maybe giving a more imperfect glimpse into things. So If you look through the literature, you'll see probably two approaches to kind of vetting our ideas. One is, well, let's prove there's something interesting happening here. Let's prove some scaling, some speed up, some efficiency gain, some advantage. Let's prove that on paper, right? And these on-paper settings might be quite divorced from real-world use cases if we ever reach them. You'll also see, and this is nice, the kind of emergence of quantum software has allowed people to run benchmarks, run numerical experiments on their ideas. So not just proposing an idea, running some lines of math, but we can also write some lines of code to try to vet the ideas that we're proposing in our papers. These are typically pretty small scale because quantum systems that we can simulate right now are pretty small scale. Quantum hardware that we have access to is pretty small scale. So these are small scale benchmarks, usually confined to a single paper testing its own results, and that's it. There's not a lot of reproducibility going on. So this is how it currently exists. I'm going to focus more on the benchmark side in this talk. And in fact, taking benchmarks from just single paper, what I call single paper benchmarks, to more of like meta study. Let's actually test a whole bunch of different numerics from different papers and compare them to each other. So if we're going to dig into the question of benchmarks, so when I say the benchmarks here, I basically mean like numerical experiments, running code either on a quantum computer or on a quantum simulator to test an idea, to validate that the idea is doing something interesting. Right? How can we, or can we even trust the benchmarks that we see in the literature already? Can we trust what we're seeing in papers? Interesting to do a kind of a small little experiment. We can search on the archive for, what do we search for here? So search for papers from the quantum physics sections of the archive, searched for the terms quantum machine learning, and then kind of a wild card on outperform. So let's look for any papers that use the word outperform plus quantum machine learning. And we found about 73 results there. I should say that using other kinds of words like better than or advantage, kind of similar results to this search. So we found 73 papers. You can break them down. About 20 we ruled out because they're just using very, very generic usage of the word outperform. Like QML is expected to outperform classical, maybe a very forward-looking statement. It's not really too concrete a thing to put scrutiny on. But then the remaining papers, they're actually talking about comparing to other models, other algorithms. So 28 of those, better than some other quantum method, right? So my turbo VQE is better than vanilla VQE. That's that kind of paper. So we found 28 of those. And then 22 papers that claim to be better than classical, right? This is amazing news, right? If we're better than classical, then that's the holy grail. Well, 22 papers are already claiming it, right? That's maybe something to be skeptical of. Found 3 papers that actually were willing to admit that they were worse than classical, right? And even on closer inspection, 2 of those papers were kind of hedging their bets a little bit. They were saying, well, if hardware wasn't as noisy, we'd be better. Or once we get quantum computers of sufficient quality, we should be better. There was only one paper out of this kind of quick and dirty search that actually just unequivocally stated, our idea is worse than classical, right? It's maybe not so surprising, right? We're incentivized to put forward positive spin, positive results on our work. That's the whole kind of the game we're playing in some sense. So yeah, there's good reason to be skeptical. There's obviously a lot of positivity if you just kind of look at the literature. And one of the messages I want to communicate here is don't take any, don't infer too much from just the positivity you might see in the literature that's facts. We should back these things up with more large-scale tests and verification and validation. So there's actually growing skepticism as well in the non-quantum machine learning community about these things. There, they actually have better tools than us to test because they have larger data sets and larger compute power. There's way more papers, so they can actually maybe look at the trends a bit more. there's clearly benefit and value in classical machine learning. It's doing something interesting for sure. But on the level of individual papers and claims made in individual papers, you want to be careful because things to keep in mind, the results of a numerical experiment may change under a whole number of factors, a whole bunch of different degrees of freedoms that you could choose to do B instead of A can potentially lead to different results. Right, so it tells you about potentially how brittle some of the results might be. So, for example, if we select a different task, then a particular model may not perform very good. If we correct for human labeling errors, we might actually not see the same performance we saw otherwise. If we use different training and test set splits for our machine learning problem, we might see a different performance. If we try to even just reproduce studies that are already out there, we might not get the same results that they report, right? So some of these results are not even reproducible. Sometimes we need to maybe use a more fair comparison, right? And if we use a more fair comparison, things don't add up anymore. There's this notion of hyperparameter optimization. There's lots of things that you kind of have to freeze in order to train a machine learning model. Well, what if you froze it to a different value? Or what if you spent more time searching for overall possible different values? You might see different performance. If you use a different scoring metric, if you don't just use accuracy but use something else, again, potentially you might change the results. If you factor in other computational costs, maybe the advantage goes away. And then this is maybe the biggest one. This is kind of leans into our study the most. There's a natural tendency in the game of science to have a positivity bias. The scientific method doesn't tell us anything about, we should be positive or negative about things. It just, you have a hypothesis and you test it, right? But in the game of science, what gets reported? What gets reported is the exciting stuff. What gets reported is the stuff that, advances our careers, makes us look like we're, putting forward exciting, interesting ideas. The null results don't always get reported. The poor results don't always get reported. And things are often not validated. So that initial positive cherry-picked result never gets kind of new data added to reweight it. So all of these things can potentially change the performance of a model. So what that means is we should gauge the performance of models, of machine learning algorithms, by varying a whole bunch of these things and seeing how well they continue to do, how robust they are, how specific or generic their powers are. So our team had the ambition, the goal, to do a large-scale independent benchmark study with the intent of judging if near-term quantum machine learning models will be useful for generic machine learning tasks. So taking a view of the literature and trying to draw some conclusions about that by testing models pulled from the literature, implementing them and testing them on various different benchmarks and data sets. So kind of before you even get to the stage where you're testing models, there's a lot of work to do to draw up the playbook, right? The rules for the study. You can't just do it too haphazardly. You have to be careful what you're doing. And there's a lot of work behind this. It's maybe not appreciated when you see at the end result, hey, we chose A, B, C, D, and E as our criteria. Actually coming up, are those things fair to choose? That's quite difficult. So there's lots of considerations to keep in mind even before we start looking at running things through the benchmarks. Okay, so first thing, what are we going to benchmark? There's lots of ideas out in the literature. There's lots of different tasks and problem classes. What are we going to focus on? We have to focus on a subset, right? So we decided to focus on quantum machine learning models that are used for classification. Okay, so not a generative problem, but like classification. Is it a dog or a cat? These kind of problems. Our starting point was the archive. We started after 2018. And the reason for this is kind of when the NISC era, the variational circuits era, kind of kick-started. So we wanted to kind of focus on those class of algorithms because those are the ones that are generating a lot of text about. Put in certain keywords, classification, learn, supervised, and this ended up getting 3,500 papers. That's way too much to test, especially when you're having to re-implement a lot of the code before you start. The code's not often available. So we have to downsample pretty dramatically still. So we decided to have some sort of arbitrary cutoff here towards influential papers, I'll call them. These are papers that are more than 30 Google Scholar citations. So these are naturally going to be biased towards more recent papers and papers that are cited a lot. But those are kind of the papers that do influence people's thinking. People will start to hear these things and think that these are established ideas. So we wanted to focus on those. So that gets us down to 561. Then of those papers, let's focus on ones that propose a new model. So not just work going back over old ideas and revising them, but something that proposes something new. And it should be a quantum model for classification on classical data, so no quantum data here. That gets us to 29. That's almost manageable. Decided to downsample that down to 15 papers randomly, just to give a random selection. Upon closer investigation, it turns out that only 11 of those papers were things that we could actually kind of legitimately or fairly implement, or that we thought should still qualify. So there might have been one or two papers that, if we were more careful, we would have selected out earlier in the process. For instance, there was one paper that actually, upon closer reading, was working on quantum data, even though that was one of the criteria we were supposed to filter for. So we ended up with 11 papers. So a couple of them got dropped in this last stage for implementation reasons. And then there was one of the papers that actually proposed two distinct architectures that are based on the same idea. So out of that paper, we had two models, and then from the remaining papers, we had one model each. So we ended up with 12 quantum models for our study. Here's a kind of a high-level overview of all of these. Don't worry too much about reading the text, but it's split into three classes. There are the QNN class, the quantum neural network class, the quantum kernels class, and the quantum convolutional models class. So quantum neural network is basically your standard variational circuit. If you know the literature, it's upload some classical data somehow into a quantum circuit, run a circuit that has free parameters, train those parameters to achieve some low-cost function value. The quantum kernels papers, or models, they have the structure where you put in use a quantum circuit basically to generate what's called a feature vector. And these feature vectors are used then just downstream in a classical machine learning pipeline, a kernel methods pipeline. So the quantum circuits are used basically just a feature embedding. And then the convolutional ones, these are ones where we actually have a quantum version of a convolutional model. So a convolutional model is a standard neural network architecture typically used for image processing. So these are the quantum versions of those ones. So those are the three classes. I don't know if everyone can read it, but you'll recognize probably quite a few kind of standard ideas that have been out there for a while. There's a few Xanadu papers in here. I think there's there's 3 papers from ours, so we're not exempt from any conclusions here as well. So these are our combatants to enter the arena. Okay. Now, once we have our combatants, who are their opponents? Who are we comparing them against? Well, we decided to choose 3 classical models to kind of match those 3 categories, the neural networks, the kernels, and the convolutions. So we chose 3 classical models, and we chose kind of standard models. We didn't choose any sort of fancy models here. We didn't make any efforts to do like a fair comparison. We just chose like, what is a standard tool that someone from classical machine learning would apply to this kind of problem? Okay, so a multi-layer perceptron classifier just out of scikit-learn, just a kind of generic one. It's the bare bones neural network vanilla architecture. There's a support vector classifier. This is a pretty prototypical kernel method type model. And then a convolutional neural network, that's a natural comparison for the quantum convolutional models. So these are all super, super standard models in classical machine learning. And we just want to see how do we compare against the out-of-the-box models. Okay, so we've got our combatants. How is the victor to be judged? How do we know who's winning or who's losing in the battle? Well, we need a problem that they're competing against each other on. So we ended up choosing 5 problem classes. They're all similar in that they are focused on binary classification. So is it a dog or is it a cat? Just 2 choices for the classification. And for training, we use the accuracy as a figure of merit. Okay, but then we have 5 problem classes. So there's a very, very simple one. It's literally just in n dimensions, draw a n-1 dimensional hyperplane. So split n dimensions into 2 half spaces. Everything in the one side is class A, everything on the other side is class B. That's how you generate that data set, and you can obviously work in different dimensions, and you can have different hyperplanes that you use to generate the data. So that's very, very simple. It's just a standard linear machine learning model should be able to completely separate those 2 classes with perfect accuracy. We used MNIST. I don't know if MNIST is the greatest thing to use for quantum machine learning, but it appears in so many papers that we kind of had to include it just for comparison purposes. We did pre-process it. MNIST doesn't typically fit into a quantum circuit that we can simulate or run on hardware, so we had to pre-process it. So we used principal components analysis to kind of downsample the dimensions there and vary the different dimensions that were available. And then we included 3 more theory-inspired data sets. So these are 2 of them are from the machine learning literature. There's this hidden manifold type of data. Basically, you generate a big cluster of data, you split it into 2 classes, and then you embed that in a higher dimensional space. We also have a 2 curves kind of problem class. Here you have some curve that kind of defines the shape of your data. And you sample points near that curve to generate the data. And then to get the second class, you do the exact same curve, but you just displace it by a little bit. And then you embed both of those 2 different classes of data into a higher dimensional space. So basically 2 squiggly lines in a larger space. And then the last one, this is one we made up ourselves. It tests a more global property, and actually it should be a challenging one, the parity of hyperplanes. So you need to know in high dimensions which side of a hyperplane you're on. Okay, so those are the 5 different problem classes. And then from those problem classes, there's a few degrees of freedom still available to us. So how many dimensions the data is, for instance, is something that we can tweak. So this allows us to kind of vary some parameters, vary these degrees of freedom, and create multiple data sets of the same problem class of varying degree of complexity. So using all those components together, we ended up generating 155 different data sets. So we have, 12 models and 155 data sets. So the servers have been humming in the background for months now to generate all the data for this talk, because there's a lot of experiments to run. And on top of that, you have to do this hyperparameter search. So there's really just a lot of numerics to back up what we'll just see here is just a few small figures. So those are our problems that we're working with. Okay, there's still a few more decisions that need to be made before we can conduct the study. You want to make these decisions in advance because you don't want to be making them ad hoc as the study is ongoing, because that can bias the earlier ones versus the later ones. So these decisions have to be made more upfront. Just to maybe spell out some of the things that you have to think about. When we work with papers, it's obvious. There's always a paper, but it's not always a code available for the paper, or the code doesn't quite match the claims in the paper, or if there's, maybe there's different examples that they had, and they don't all allow us to compare against other models, or it doesn't obviously fit into the 155 data sets that we've created. So there's always some tweaks needed. There's always some implementation things needed. We tried wherever possible to be as faithful as possible to the existing code, to the existing papers, but there's some decisions that had to be made, and we just tried to use common sense whenever possible to fill in the blanks. Some models take a lot longer to converge than others, so you have to maybe set some criteria. We just basically let them take as long as they needed. We just waited until they settled in and stopped changing after a couple intervals, and then we said, okay, you're done training. But some might take 30 seconds, some might take an hour, and we let them take as long as they needed. We didn't factor in training time as kind of way to limit models. You might have to do this hyperparameter batch size. When you're doing stochastic gradient descent, you have to choose what are the size of the batches that you're stochastically selecting from the data set. We didn't optimize this hyperparameter, but we actually had to use it as a way to control the length of computations, because if you keep it too big, some of these computations take way too long. So this is one that we kind of kept in our back pockets. It's not optimized for best performance of the model. It's optimized for just numerical implementation reasons. Sometimes there's data preprocessing needed. We tried to preprocess and scale things into some meaningful interval whenever possible. And then you have these choice of hyperparameters. Despite your model being fixed, there may be still a few free parameters that need to be chosen for a particular experiment. And ideally, you should iterate over these and test if I fix this one hyperparameter, and I train the model, and I look at its performance, and then I change that hyperparameter, and I train the model, I look at the performance, what's the best choice out of all of those experiments? So we had to kind of make a grid to search over all these different permutations, and we tried to take choices that are relevant to the paper, tried to use common sense, and also, again, this is one of those things where we had to eventually set a limit on the runtime, so we can't do a super exhaustive search. So those are the kind of things that you'll have to take into account when you're designing a benchmark study. Maybe just as a quick teaser now, the hyperparameter optimization actually, these are results. Don't read too much into the numbers here, but just look at the size of those bands. So what those bands indicate is the best performing model versus the worst performing model for the same model type. So it might be a very specific model from one specific paper, but we change the hyperparameters and we look at the performance, and you might get between a random coin flip all the way up to perfect accuracy. So it's quite important to do hyperparameter optimization. I don't think most people are doing those in their own papers, but it turns out it's quite important, because the performance claims that you can make are really dependent on your choice of hyperparameters, as we can see by the large spread here. All right. So that's all the setup. Now we can get into the actual results. What did we find? So the way I'm going to present this, we have 155 different data sets, and we have 12 different models, and then we have 3 classical machine learning models. So I'm going to treat it like the Olympics. So we have the Olympics, you have maybe 500 events, right? And you have 150 countries participating. So our models are going to be the countries, and the events are going to be the different benchmark data sets that they're run on. And so who wins? Well, the one who has the most gold medals is usually categorized as the country who's won the Olympics, right? You have a ranking in the online or on the newspaper that says, Canada has 12 gold medals and 8 silver medals and 6 bronze medals. So that's how we're going to kind of compare models to each other, is who's winning the most gold medals. That tells us which models are kind of most generically powerful versus ones which maybe just won that one esoteric medal in breakdancing. Okay, so these are kind of the ranked results split into 3 classes. So there's the kind of neural network class, the support vector machine class, and then the convolutional class. The real main thing to notice here is the top line is the best. It's always the classical one. So the one with the biggest green bar is always going to be the classical model. That's what we've discovered. That's kind of our first takeaway here. Some quantum models actually did okay. They won a fair share of events. So that's cool. Some of the quantum models may be doing something interesting, right? Some of them did really bad, and you probably are not going to be contenders for even making the cut for the Olympics next time. So that's kind of the main takeaway for this slide, is that the pretty out-of-the-box classical models over a wide class of problems, sizes, and types, they performed generically better than the quantum models. Getting a bit more into some of the data here. So we've got one of the data sets, the linearly separable data set. On the left side, we show the quantum neural network class. On the right-hand side, we show the support vector machine class. The lines at the top are the classical models, and the x-axis going from left to right is basically the dimension of the data sets. So it kind of gets harder and harder as you go along. But you can see that the quantum models actually get poorer and poorer as you get higher dimensions. So if people are only running small-scale benchmark experiments, they don't go up to higher dimensions, they may make false conclusions about the power of their model. This is on the MNIST data sets. So the left one is this neural network class, the right one is the support vector machine class. Again, we see the classical model at the top, and kind of the performance peaks for all the other models, except that's tree tensor classifier, which doesn't seem to be doing well at the bottom there. I should say these are kind of representative benchmarks. Other benchmarks that I'm not showing you give very similar types of results. This is the last problem, which was hyperplane, the problem. This is one where I actually expect by design that both classical and quantum models are going to do poorly. So we kind of designed this one to be difficult as the dimension scales up, or as the number of hyperplanes in this case scales up. And it's kind of what we see. The classical model still generically is the black one on top there. There's a few peaks where the quantum model might pass over and do slightly better for one particular dimension, but then it oscillates back down again. So the main takeaway here is even though there's some variations, the picture is generically consistent, that the quantum models don't do well as you scale up, and also similarly the classical models do the best. Okay, so those are the results. If you're interested in more and more in-depth stuff, we'll be sharing all the data, we'll be sharing all the benchmarks and the code for running those things. The last part of the talk I want to get into, what is going to happen next, right? We've done some studies. I think the purpose of benchmarking should be to make us question our assumptions, but also it can reveal things that we may not have thought about otherwise, because we're testing things in a richer manner than we would have done otherwise. So the benchmarks actually do reveal some interesting open questions which one can consider for follow-up. And we'll have the data all available, and if other people want to look into the data and find their own open questions, we encourage people, because we don't want to be completely doom and gloom and say that classical models are just hard to beat and we haven't done a good job yet. There's some interesting data points here that are maybe worth following up on. Okay, so one question someone might say, it's often claimed that entanglement is one of these mysterious quantities in quantum computing, and that's why we expect QML to do interesting, advantageous stuff, because it has access to entanglement. Did a very simple follow-up experiment where we created a model that was just a standard variational circuit, so a quantum circuit with gates and measurements. And those gates are parameterized, and you can tune the parameters to minimize the cost function. But the structure of the circuit was such that there was no entanglement generated. So the gates are only ever being applied on the single qubit level. No qubit ever interacts with any other qubit. Well, how does that model do? Not bad, actually. It turns out it does better than some of the other fancier quantum models. So that's interesting. That's something to maybe generate some follow-up questions, right? Why, if we're always claiming that entanglement is this important, crucial ingredient for quantum models, why does removing it do little harm? So if you're looking carefully at this graph, maybe it's hard to see the colors from far away, but there's a couple quantum models in there that are between that separable classifier and the fully classical one. Right, so what about those two? They seem to be doing all right. They're almost doing as good as the classical model, and they're doing better than the unentangled one, so surely some entanglement is crucial there. Well, you take those two models, they're very specific ones. They're the dressed circuits model and the data re-uploading model, two kind of standard models you see in the literature. And you'll take those architectures and just remove the entanglement, what happens? Well, for the dressed quantum circuit classifier, turns out it doesn't change the performance at all, so that one doesn't seem to be relying on entanglement. The data re-uploading classifier actually does get worse. So that one maybe seems to be using entanglement somehow for its performance. Still not beating classical, but maybe there's something there to that idea that we're hearing in the literature that entanglement is important. But only for this model. It doesn't seem to be validated for some of the other models. Okay, so what makes that data re-uploading model kind of successful? This is actually one of the earlier models proposed. It has a couple of unique ingredients that distinguish it from other models. It has a circuit that looks like this, and you alternate between uploading your input data and having a parametrized layer in your circuit. So X is the input data, theta is the parameter, and you alternate. That's why it's called re-uploading. So that's one unique feature here. Another unique feature, and this was surprising to me that more models don't do this, but they include that you can reweight the data as you're uploading it. You can have a parameterized weight attached to each data point. The third kind of unique ingredient here is they use a specific cost function that's not too common in the rest of the literature. Okay, so you can perform a study on that and say, well, those are the three ingredients. What happens if we remove those, right? Let's do an ablation study. So looking at the results, turns out if you remove the cost function, the special cost function, and you put a standard cost function there, it doesn't really change the performance. So that one doesn't seem to be too important for performance. However, if you remove either the scaling that you're doing to the uploaded data, the trainable scaling, or if you're removing this kind of re-uploading structure where you alternate and you just do all of your data upload all at once and then all your parameters at the end and you don't cycle back and forth, if you remove that, it also hurts performance. So those kind of hinted, well, those are two interesting ingredients here, right? Those are actually responsible partially for the performance. That's an interesting open question, right? That's something that came out of the benchmarking study. By looking a bit closer on these models, we can actually try to understand of all the random ingredients that a model might have, which are the ones that are actually doing something interesting. There was another model there, the dressed quantum circuit classifier. This one's a funny one. You basically take a neural network that's pre-trained and you chop out like a middle layer and you replace the middle layer with a quantum circuit. And my conclusion to this model is that doing that doesn't hurt anything because the performance of the model ends up kind of being the same in the end. It's maybe not too surprising because there's so much huge work being done by the rest of the layers there, and the quantum circuit is just kind of, it's not hurting anything by passing through it, but it's not contributing anything. So yeah, we can say, well, that's kind of a prototypical hybrid model. So do quantum layers and hybrid models, are they doing something interesting or are they doing something kind of standard? So what we did is we looked at all the different layers of the model, and then we also looked at the comparable structure without the quantum circuit removed and look at all the layers there. And we kind of mapped in low dimensions what's happening to the data set as you go through each layer. So the one I want to draw your attention to is this one here. This is kind of where the quantum layer is inserted or not inserted on the bottom one there. And we can see they're slightly different. They're qualitatively doing something slightly different, but not too different, right? They're still able to separate the red and the blue curves. They're not mixing them up too much. Actually, the quantum one is maybe doing it a bit more, but it's not something that the final layer of the neural network can't recover from. As we see in the last column there, it's easily able to recover from that. So that's why it doesn't hurt. So again, this is one of those things where you can do studies to compare by just removing certain components of a model rather than comparing your full model versus a fully classical model. Final open question could be that sometimes the quantum kernel methods actually perform somewhat similarly to the classical models. And why is that? Well, this is another one where we kind of looked at it a bit more. This is in 2 dimensions. These are kernel models, so we can look at a kernel function, which is a 2-dimensional function. And on the left column is the classical one, and then all the right columns are the quantum ones. And we can see in the first row that they're all kind of the same shape. So that's probably why they perform similarly, because they have the same kind of structure to them. The lower one's a bit different. You can see that the quantum models start to do more and more funky things there that are quite different, more spiky, especially the projected quantum kernel model. So this at least reveals some sort of specific property of that model that warrants further study. It's doing something different than the classical model. I should say in higher dimensions, these things don't map so nicely. So also it might be something that's different between low dimensions and higher dimensions. They're not, they're not looking exactly the same in higher dimensions. So again, open questions that doing these studies more systematically can help unearth and can help us understand these models better. So just to conclude, I want to give you the key takeaways from this talk. Number one, full credit to our team. Designing good benchmarking studies it's hard work. It's nasty work. It's not fun. But we're happy to do it because if it helps move the field forward, it helps people thinking and seeing the right things, it's worthwhile. Next point, this is probably the only one that people will take away, I would guess. Classical models, standard ones, typically outperform even the most influential quantum models. So there's still lots of work to do here to really make our case. Another one, that fancy phenomenon of entanglement. I don't know if we can make the case that it's doing anything. We can always appeal to it, but the numerics do not necessarily back it up yet. We need to make a stronger case that that's to hold. And there might be some models where we can show that. And then doing this kind of benchmarking, I think, helps us move the field forward because we're not just focused on what's a cool new idea, but actually what's a valid idea? What's an idea that's working, right? And then maybe it's the more boring march of science doing this, but I think it's more important for the field because otherwise you end up being disillusioned if you end up working on all these ideas, but they're on paper, they don't actually work in practice. So I'd rather know that in advance, I'd rather know that soon rather than working on false assumptions. So definitely doing benchmarking studies like this is important for science, is important for QML, and we hope it can help advance the field's thinking in the future. Thank you very much.
Cool. All right. Thanks, Nathan. That was good. We're going to get some questions from the in-person audience. So, yeah, raise your hand if you have a question, and Catalina will hand you a mic. Catalina, do you want to just make sure that one works? Turn it on and...
Test.
Hey,
yes.
Sweet.
Hello. So I was curious. You said in the conclusion that entanglement is not very interesting and it doesn't really change the model, if I understood right. Yes?
More or less, yeah.
But I was curious and more like the study was for accuracy, but in other terms like robustness against adversarial attacks or generalization, would you think that entanglement would help in those terms?
To be honest, I don't know. I mean, I think this is the kind of thing that we can test. We can try to look at measures for those quantities and see. We've got all the models built now. We can just test those entangled models and non-entangled models against those. I'd find it hard to predict, to be honest. Like, I would say removing entanglement, I would guess. I don't have much intuition whether having entanglement there makes it more robust.
Yeah. But because I was curious, like it was just analyzed in terms of accuracy, but maybe entanglement or like hybrid networks, like you were saying that there wasn't much change, but maybe those evaluation technique or like a robustness and things like that would increase.
Yeah, absolutely. It's a valid hypothesis, and we'll have all the data, all these models available, and it's something that people can test. So I encourage people to check that out if they have that hypothesis.
All right. Thank you.
Hey, so I know you talked about the MNIST data set, and obviously you were compressing it or basically downscaling it a lot so you could actually make it fit in the machine. But do you think that if basically you were able to encode more data, would the performance be, do you think it would be better, or would it be possible for it to be better, or do you think that's kind of just, would it just like comparably to a classical system at that point? Because obviously it kind of did worse at this point, but you're losing a lot of data just in downsampling, so.
For sure. I think we can kind of infer from this slide here that the quantum models aren't getting any worse as we're increasing the so the x-axis here is basically equivalent to like how much we downscale the images and how much information we include. So they're not getting worse. They're not getting so much better either. And that's because when you're doing this principal component analysis to downsample the image, it's kind of marginal gains every extra dimension. Most of the information in MNIST is in the first 5 degrees of freedom or something like that. So yeah, it should get better, but maybe just marginally.
Okay.
Yeah, so Catalina's coming around with the mic for you there.
Hi. So have you tried changing some of your crucial decisions, convergence criteria, and see how, the results change, or if the entanglement properties, how they changing the convergence, or for example, convergence criteria, or some of those crucial decisions can affect those results as well?
Yeah, to answer the question, no, we haven't specifically gone back and rerun a new set of benchmarks with those criteria now switched. There were some things we kept fixed and some things we didn't. But we did initially start, we didn't, there are some decisions you can only kind of come to by getting your hands dirty with the data.
I mean, obviously, just certain.
Yeah, so there was some early just digging into the data a little bit to help infer what decisions we should make, to help uncover those crucial decisions. But then once we did, they were locked in for the rest of the study.
Oh, okay. Thank you so much.
So to perform the QML algorithms, were they either performed on a simulator or an actual quantum computer?
Yep, all on pure state simulators.
And so, okay, that was my question. So the assumption was there was no noise doing this. Okay.
Correct. Maybe one last question, yeah?
Can you elaborate on the case where you said the data set is more difficult for classical machine learning as well? To what extent, what make it more difficult? And whether, depending on the problem set you're working on, maybe some cases QML could perform better. It's just a lot of the cases you're testing on is already working well in classical machine learning.
Great, thanks for the question. See if I can find my slide here. So the data set you're referring to is this parity of hyperplanes one. And the reason this one is expected to be difficult for classical and quantum is that it's parity is like a global property, and it requires kind of global information. And so with limited data, it's hard to make a good guess there. So that's kind of unique to both classical and quantum. It's not something we would expect either one necessarily to perform better at. The hidden manifold and the two curves, these are just pretty generic ones. These are not specifically designed for real world data. These are kind of just to test test settings that are believed to hold about any sort of structured data, right? So I would say the main thing that's maybe is not specifically represented here is what if there is a quantum data, so a data that specifically showed correlations that were expected to be good for a quantum computer to do. Yeah, it wasn't included, but that's a good suggestion, yeah.
Okay, we'll get one question from the chat here, and then we'll have to wrap it up.
Sorry, guys.
So we have a question on Twitch from D'Amelio. One thing that is not entirely clear to me is the quantum classical comparison done to see how quantum-inspired models work instead of using actual quantum circuits? We know that data encoding is expensive, so why are quantum models helpful to classify classical data?
Well, maybe they aren't helpful. That's maybe something a lot of people might tell you. Maybe that's a conclusion that can be made, right? If it merits further investigation, but maybe these are the wrong types of problems to be probing quantum models on, right? And I've talked to a number of people who, they're strongly inclined to dig into, well, I think the quantum data is the real kind of killer app for QML, and that's a completely fair hypothesis, and I kind of share that belief.
Okay, cool. Well, one last round of applause for Nathan. Thanks so much, Nathan. Really appreciate your time here.